Okay, responding to a good question about the nature of the solution in this case. Your solutions are going to be x equals a e to the RT, okay? So that's AE to the negative gamma over 2m, okay? And what we do is we factor the gamma over m out of this, giving us a gamma over m times 1 minus 4km over gamma. Okay? And so I don't make some stupid mistake. I'm going to write it out a little more carefully.
Okay.
And then, you see, so I'm going to write a 1/2 here for the 2 and not complicate my life trying to remember where the 4 goes over here. Okay, but it's going to go here and there's not going to be 1 here. Okay, but I don't want to make that assumption. It seems obvious. But so it's going to be plus or minus the square root of 1 minus 4 km over gamma times t. 2 solutions. Okay? And let's just, and it's 1 plus or minus this times t. Okay? Left out the 1. But obviously, you factor out the negative gamma over m, you're going to get a 1 here. When you factor it out of this, you get this. So if you multiply back through, you should get this. Well, multiplying negative gamma over m through the square root, or gamma over m through the square root, gives you gamma squared over m squared here, and gamma squared over m squared here, and I did have a mistake, because I guess I got to have a gamma squared there. Okay? Now if I multiply this by gamma squared over m squared, I get 4k over m, which is what I've got there. So that's just simple algebra, but you got to be careful. Okay? And I left out the square of the gamma and then just write down that 1. So you got to be careful. And I'm going to now write this as AE to the negative gamma over 2mt times e to the plus or minus I'd have to have a half out here because of this half, but instead of having the half out here, I'm going to put it in here, and it's going to give me a 1/4 minus, nah, I'm going to leave it out here. And I'm going to write it plus or minus 1/2 square root of 1 minus 4km over gamma squared t. Okay? Now, if this is a discriminant here, is positive, then I can just keep it in this form because I got two real solutions. If it's in this form, I've got an oscillatory solution. Okay? So, if four km over gamma squared is greater than 1, you have this, which you have in any case, whether it's greater than 1 or not. If it's greater than 1, that makes this negative. Okay? And this equals A e to negative gamma over 2m t times e to the plus or minus omega t okay? And, you know, this could be rearranged. You go through the 1/2 and stuff like that. You're going to get a 1/4 here. You're going to get a 4 km over gamma squared here. But your test, of course, is whether this is greater than 1 or not. Okay? So you have this. Or this, by Euler identity, which you should understand through understanding Taylor series and the Taylor series of the exponential, sine, and cosine. Okay? Didn't really have that down last time I looked. And it's a very important identity, because if you don't know that identity, the entire universe collapses.
Okay.
Okay, no oscillatory motion. We're done. Okay. Right? My explanation. A is a complex arbitrary constant, which implies through manipulations that I showed you that you don't necessarily have to remember, but you better remember the results. And when we're tested over this, over second order equations and Laplace transforms and stuff at the final, and higher order equations, you need to be able to fill in why you get the B and the C and how they're related to the A that you have there. Okay? So you have these solutions. Okay, well, that's a product of this and some oscillatory solution, or and this is just basic high school trig, okay? And I left out my integration constant at the beginning, so I better erase that. And this A here, I want to use the symbol, but it's a different A from this one. Okay? And this is a solution you would generally do. Now, cosine of omega t plus phi is just a horizontally shifted cosine function, so you can have any phase at t equals 0 that you like. Okay? And this is just an exponentially decreasing function. So what you have is a product of an exponentially decreasing function and some kind of a cosine function. It starts with some phase.
Okay. So it's decreasing in the y.
Decreasing in amplitude.
Okay. Yeah.
And that's like your pendulum in water. Goes and then
Yeah.
not as far, and then not as far, and then not as far. Pretty soon it stops.
Okay.
Okay? And of course, an exponentially decreasing function would never actually stop. Okay?
Okay.
But once a thing oscillations down to Planck length,
Mhm.
10 to the negative 34 centimeters, really, really small,
Yeah.
then essentially there's no motion. And there are other factors that cause it to stop well before that.
Mhm.
But your basic model, your ideal model, would be this kind of a function. Okay? And since it's exponential, it is going to decrease to Planck length before too long.
Mhm.
It might be a few minutes, but
Okay.
it'll get there.